This section of 6.1 deals with slope fields. Sometimes when you go to find a differential equation analytically, it can either be really, really hard or even impossible to find. When this occurs, if you go and you look at a graph, sometimes you can learn a little bit about the solution to your differential equation. If you want to start off, let's consider the function y prime equals f of xy, where f of xy is some expression given in terms of x and y. At each of these points, so we'll say at each point xy, where f is defined, the differential equation determines, sorry I ran out of room there, but determines the slope y prime equals f of xy of a solution at that given point. Okay, if you draw line segments, at selected points, and in this case we're going to say xy, in the domain of f, so in the domain of f, the line segments form what we call a slope field, so a slope or direction field. And we'll go over what these look like here in just one second. And last but not least, a slope field shows the general shape of all solutions Okay, so this is not a particular solution, but it will be all solutions. And it can be useful in getting a visual perspective. So in getting a visual of the directions of the solutions of the differential equation. Let's look at our first example, or in your notes, it's going to be example 3. For example 3, we are going to sketch the slope field for the differential equation y prime is equal to x minus y for the points -1, 1, 0, 1, and the point 1, 1. The first thing we need to do is we need to evaluate our equation y prime at each one of the given points. So y prime of the point negative 1, 1 is equal to, if I plug negative 1 in for x and I subtract the positive 1 in for my y, this here is going to give me a negative 2. Next, I'm going to go in and evaluate y prime at the point 0, 1. This is going to give me 0 minus 1, or a negative 1. And y prime of the point 1, 1 equals 1 minus 1, or 0. Now that I have all of those points evaluated in my function, I'm going to go and I'm going to graph this. And because I'm going from negative 1 to a positive 1, let's see, I have negative 2, negative 1, positive 2 here, and a positive 2 here. Now at my point, negative 1, positive 1, that's this point right here, I see that I have a slope because my y prime value is equal to a negative 2. So I'm going to come in and I'm going to approximate a slope of something that looks like a negative 2. Then I'm going to do the same thing, except at the point 0, 1, I'm going to come in and I see that I have a slope of negative 1, which isn't quite as steep. So that slope might come in and be a little bit less steep than the previous slope. And then at the point 1, 1, which occurs right here, I see that I have a slope of 0, and hopefully by now we know that a slope of 0 is just a horizontal line. So these are the three slopes that are given at those given points there. Now, we do have an example 4 and an example 5 that we will go over tomorrow together in class. And for example 4, if you want to look on page 408 of your textbook and kind of look at those graphs, we'll touch base on that tomorrow. And then I'll also go over how to sketch an actual slope field with you tomorrow in class. But I think that would be easier to do in person rather than in an online setting. So the last thing we're going to look at out of section 6.1 is what we call Euler's method. Okay, and Euler's method is another like an approximation method. It says if you're given a differential equation, okay, like a dy dx equation in the form of f of x, of the point xy, and some initial condition, then Euler's method says that we can approximate a solution by a linearization equation. And I'll give you the equation here in a minute. But essentially what you've got is you have some graph that looks like this with a given function, and you're told that you have a point right here, and that point corresponds to some y value, which is y sub 0, and some x value, which is x sub 0. And this equation here was y equals y of x. Okay, now we have a point, or a tangent line, I'm sorry, that goes through this point to this graph, and that is given to us by the equation y equals L of x. And this is just our linearization equation. The other thing about Euler's method is it's a good approximation tool if you're looking at short intervals. You're not going to want to do something over the span of like 100 units, but if you're looking at really tiny units of change, then this is an okay approximation method to use. The main idea is to connect a string of little tiny line segments to approximate the curve over a longer stretch. Okay, and I'll show you what I mean here in just one second. Okay, if we redraw this graph here, and like I said, we're given some point, some function that looks like this. I have x sub 0, y sub 0. What we're going to do is we know that this point here x sub 0, y sub 0 is a solution on the curve. If we specify some new value, x sub 1, okay, and let's call x sub 1, let's see, we have our tangent line here. We're going to pretend that it was tangent through the point. And I identify x sub 1 as some point on that line. So I'll come down here and call that x sub 1. Then I can say that x sub 1 is equal to my previous point, x sub 0, plus some arbitrary distance here, which we're going to call h. So we'll say plus h. Okay, and h is some really small, tiny increment. So if I know that that's what x is equal to, I can now go in and find my y1 value by plugging in what I know for x and y. So this is going to give me y is equal to, oops, I apologize, my y sub 0 value plus my function evaluated at my x sub 0, y sub 0 value, okay, times my h, okay, and this function will be given to you. And if you notice, when I'm looking for my y1 value, I'm actually using my previous x sub 0 and y sub 0 values to plug into this. Okay, what this does is that this generates a point that is very, very close, okay, and as you can see, it's very close to the curve. So if we come in here and look in this region, we see that this point here is really close to that corresponding value right there, and that's where the approximation comes in. Now if I go and use my new point, x1, y1, and the slope, so I'm going to now use x1, y1, and the slope of my function f of x1, y1, of my solution curve, we can now set x2 equal to my previous point, which we found in x1, and add h to it, and use the linearization of the solution curve through that point x1, y1 to get our y2 value. And our y2 value now is going to become the previous y value, which was y1, plus my function evaluated at x1, y1, all multiplied by that h value. Now my y3 value, without going into too much of a repetition here, y3 then, you can predict, would be my y2 value plus my function evaluated at x2, y2 times my h value. And the pattern will continue depending on how many linearizations you want to go through. If we go back to that original curve that we had, once we do all of these linearizations, we pretty much end up with something that looks like this. Your original curve is going to look like this. Okay, so this would be the true solution curve. You have your x sub 0 and your y sub 0 value. And you're going to start out by finding the tangent line to this point. So your tangent line, I'll get better at this, guys, is going to be something like this. Okay, then you're going to take that curve. We're going to go and we're going to find an x1 point, which is going to be here. That's going to hit this point here. So this is my x1, y1 point. Now I'm going to go and I'm going to find the tangent line through that curve, which is going to kind of veer off this way. I'm going to go and find another point, which is my x2 value. Okay, and I'm going to go through and do the same process. I'm going to go and I'm going to find the tangent. Oops, actually, let's relabel this. This is x2, y2 here. I'm going to go and do another point of tangent C. And I'm going to go through and do the same thing. And I'm going to predict my x3 value. So as you can see, oops, and this is going to give me my x3, y3 value. Okay, and as you can see, all these distances in here, they're getting greater. And I have this kind of blown up just for an exaggerated purpose, just so you can see. But in theory, if your x values are all really close to each other, these are going to be really minor differences between your original curve, which is this curve here, and your new tangents that you're creating with your y prime equation. So let's go in and look at our first, or I guess the only example that we're going to do with this. Okay, I think that this was example 6, since we're going to do 4 and 5 tomorrow in class. So say example 6. This says use Euler's method with a step, and a step is another term for an h value. So with a step equal to 0.1 to find the first 3 approximations for the initial value problem. And the initial value problem is y prime is equal to x plus y, and you're given that y of 0 equals 1. And you are to start at x of 0 equals 0. So the first thing you want to do is you want to find your y sub 1 value. And you do that by using your y sub 0 value plus your function evaluated at x sub 0, y sub 0, and you're going to multiply that by your h, or your change in x's. So now to find y sub 1, all I'm going to do is I'm going to go in and I'm going to plug in everything that I know. I was given in my initial condition here that y sub 0 is equal to 1 plus my function evaluated at x sub 0 and y sub 0. So I'm going to go x sub 0 into this equation is going to give me 0 plus my y sub 0 value was 1. And now I'm going to multiply by my h, or my step, which is 0.1. So when I simplify all of this, I have 1 plus 1 times 0.1, which is going to give me 1.1. So that's my first approximation. My second approximation then is going to give me y2. And y2 then is going to use my previous term, or my y1 term, and I'm going to add that to my function evaluated at x1, y1, times my value of h. So again, I'm going to go in and I'm going to plug in everything that I know. And in this case, I know that my y1 value was 1.1 plus my x value, or x1 value, which is 0.1. Okay, and I got that. Maybe I should do that here over to the side. X sub 1 is equal to x sub 0 plus your step of h. So this is going to give me my x sub 0 value is 0 plus 0.1, which gives me 0.1. So that's how I got this 0.1 here. And I'm plugging that in for x. Then I'm going to go plus my y value, and it has to be y1 in this case. So I'm going to plug 1.1 in. Multiply it by your change in x, which is 0.1. And this gives me, once I simplify it all down, 1.22. Now, to go and find my y sub 3 value, I first need to go, or I'm going to take my y sub 2 value and add it to my function. Oops, just 1 second here. I apologize. Oops. Here, we're going to redo. Let me get back to my eraser here. And I guess it's not going to let me erase it. Okay, so let's just make this an f of x sub 2, y sub 2, times your change in x, or the h value. We know my y sub 2 value was found from this up here, so I'm going to go 1.22 plus my function of x plus y, except now I'm going to evaluate that function using my x2 and y2 values. Well, to find x2, I know that this is going to be equal to x sub 1 plus h, and x sub 1 was 0.1 plus my h value, which is 0.1. So my x sub 2 value is really equal to 0.2. So when I come over back to my equation for y3, when I go to plug in my x sub 2 value in for x, I'm going to plug in 0.2 for x, and I'm going to add that to my y2 value, which was 1.22, multiply that quantity by my h value, which we know is 0.1, and when we simplify all this, I got 1.362. So this here would be the third approximation using Euler's method. And I think that's probably where we're going to stop for today. So hopefully this went okay. Any questions that you have, please bring them with you tomorrow, and we'll go over them in class. Thank you, and have a good night.